Today's speaker is Tim Hollowood from Swansea on the solution to the faster than light puzzle and using a new technology for us, I think.
Yeah, okay, thanks very much, Neil. So I want to talk about a puzzle in quantum field theory, more specifically QED, that was invented in Cambridge many years ago, over 25 years ago. So it seems fitting to talk about it in this program. So this is work in collaboration with Graham Shaw, who has been pestering me for what seems like years to get interested in this problem. And this year I finally succumbed, and we think we now have the solution to this puzzle. Okay, so I'm going to use this new technology, the notebooks. I give all my undergraduate lectures this way, but this is the first time I've given a research seminar, so you'll have to be, you will be the guinea pigs to see whether this works. Okay, so let me give a bit of motivation, what we're trying to do here, or if you like, the bigger picture. The reason why I got interested in it was this idea of what kind of constraints you can put on an effective field theory. So constraints on effective field theories that come from having a good UV completion. So the idea is that there may be many effective field theories that look perfectly good as effective field theories, but they just don't admit some kind of good UV completion. And in particular, so it's to do with the issue of UV completion. And in particular, it's to do with issues about causality in the effective field theory. So issues regarding causality. So it's been suggested that if you look at an effective field theory, that if that effective field theory has what we call superluminal propagation, so I have to be careful here, I'm talking about QED, I'm talking about photons. So photons always move with the speed of light, of course. So superluminal in this context means that the velocity is greater than c. Okay? So this is about issues regarding causality, and in particular issues regarding the phase velocity that we calculate from the effective field theory for the propagation of various modes. And the idea is that if this is greater than c in the effective field theory, that this could signal the fact that the effective field theory is sick and doesn't have a good UV completion. So rather than talk about phase velocities, I can also talk about refractive indices. They're just the inverse of the phase velocities, or rather their real part is. So the phase velocity being greater than c is the same as saying the refractive index, or the real part of it, is less than 1. Of course, the refractive index can have an imaginary part which corresponds to absorption. So these are the issues I want to think about. And I want to think about these issues in the context of QED. So this is the faster than light puzzle that I alluded to. But before I do that, I just want to point out that issues about causality are not really addressed by thinking about an effective field theory. In other words, in an effective field theory, this frequency here has to be taken to be small, whereas really the causal structure of a field theory is to do with the UV. It's to do with the high frequency behavior. And why is that? Well, one way of thinking about that is if you think about what causality means, let's imagine we have a field which vanishes, say, to the right of some point, and then has some arbitrary shape to the left. Then causality, or one aspect of causality, is simply how fast does that blob of field move? So what's the velocity of this so-called wavefront here? And you can show that this so-called wavefront velocity is equal to the infinite frequency limit of the phase velocity. And the reason why that is that in order to get a very sharp theta function-like behavior for the field, you need very high frequency modes. Okay, so that's the intuition. So really, issues about causality can't really be addressed in the low energy theory anyway. Okay, so that's an important point, that really to talk about causality, we need the phase velocity or the refractive index, not just at low frequencies, but in fact all the way up to infinite frequency. However, there is a relation between the phase velocity or the refractive index at low frequency and the refractive index at high frequencies. And that comes from an old style dispersion relation. So the so-called Kramers-Kronig dispersion relation. So what's that dispersion relation? Well, it's derived by just taking the refractive index in the frequency, complex frequency plane and integrating it along a particular contour. So a contour that goes just above the axis, jumps over a pole at 0, and then is completed at infinity in the usual way. And the integral that I'm thinking about here is omega, d omega over omega of the refractive index. So clearly there's a pole at 0, that's why I have to jump over it, and there's a pole at infinity. So assuming that the refractive index has no poles or other singularities in the upper half plane, I get a relation that says the real part, so then I take a real part, of the refractive index at infinite frequency. So that's the contribution from the semicircle at infinity, equals the real part of the refractive index at 0 frequency minus the integral coming from the integral along the real axis, that can be written as an integral over the imaginary part of the refractive index. And the imaginary part is conventionally an odd function, so I can write it as an integral from 0 to infinity. So this assumes analyticity. So that means that the refractive index, or more generally a Green's function, has no singularities in the upper half plane. And this relationship between causality and analyticity runs very deep in quantum field theory. Now, usually this imaginary part here by the optical theorem is related to some total cross-section. So this is positive. So you can see that if that's true and all the assumptions that go into this dispersion relation are valid, then it tells me that if the real part of the low frequency refractive index is less than 1, so in other words, if the effective field theory has some superluminal propagation, then that implies that the real part of n infinity is less than 1 as well. In other words, that this wavefront velocity is greater than c. And then I have potential problems with causality. Okay. So all this is directly relevant to the puzzle, because the puzzle involves QED in curved space-time. So this goes back to 1980, not 1986. 1980, a result of Ian Drummond and Hathrell. So they considered QED in curved space, and they showed that quantum effects gave you a low frequency phase velocity which is greater than c, or a refractive index at low frequencies that was less than 1. Okay.
Have something to do with breakdown of unitarity, which you would expect in effective field theory?
Well, those issues about unitarity. So the point is, we have to, since we're going to find this puzzle, we have to sort of think about all the possible ways out, and then that's one issue. You know, what about unitarity? What about the optical theorem? Is the imaginary part of the refractive index greater than 0? So we have this puzzle which I'll sort of show, and then the point is that you can only solve the puzzle by doing a real calculation, and then we do that calculation, we solve the puzzle. So it turns out there is no issue with unitarity, and there is no problem with the optical theorem. So that'll be the conclusion. Okay, so in QED, so we're thinking about the propagation of photons, and of course a photon in QED can sometimes turn into an electron-positron loop. This is a one-loop correction to the propagation, to the vacuum polarization of the photons. Now in a curved background, the point is that the electron loop here has some finite size, so it kind of feels the curvature, the local curvature of the space. And so there are corrections to the propagation involving the sort of interaction, if you like, between the loop and the curvature of space. So these terms, the relevant terms in the effective Lagrangian, look as follows. So we have the conventional Maxwell term, and then it's a one-loop effect. So there's the fine structure constant. There's some numbers which don't really matter. Well, they do. 720 pi squared. And then there's the mass m of the electron. And then the two relevant terms are couplings between the curvature and two powers of f. So one term involves the Ricci tensor and has that form. So that term will obviously affect the propagation because it's got two powers of the field strength. And then there's a term which is -2 and involves the Riemann tensor coupling to f. And then there are other terms, but they don't affect the propagation. Like there's a term involving the Ricci scalar, but that's not relevant. So these are the terms that Drummond and Hathwell wrote down, and from this you can calculate how this changes the mass shell condition for the photon, and from that you can extract what is the low frequency limit of the refractive index. And of course that depends on what space you're looking at, because we've got the curvature there. So different spaces have different behaviors. So two examples which just illustrate what's possible if the space is conformally flat. So the Weyl tensor vanishes, then the refractive index in that case is just proportional. So this is the refractive index for low frequencies. Okay, and I'll talk about a bit more about why that's true in a second. So this is proportional to the identity. So I and j here, so let me have a little bit of notation. My photon's moving along classically a null geodesic, and let u be the affine parameter along that geodesic. So that, let me think about that as one coordinate in this space. There are two orthogonal coordinates to the geodesic, other than u itself, because it's a null thing, u is null to itself. So there are two orthogonal coordinates, y1, y2, so yi if you like. So I and j run from 1 to 2. They describe the orthogonal space where the polarization lives. So the refractive index is actually a 2 by 2 matrix in general. So this is 1 minus 11 alpha 180 pi squared m squared times the components of the Ricci tensor are uu, where u is the direction along the null geodesic. Now, by the null energy condition, this has to be positive. This has to be greater than 0. So you can see that what we have here are two polarization states with a refractive index less than 1. So this has two superluminal polarizations. Okay, so that's just one particular example. Another example is a Ricci flat background. And so in this case, the first term vanishes. First term up there. And in that case, you get birefringence. So you get two polarization states with different refractive indices. And if you work out the details, you have one superluminal polarization and one subluminal. Okay, so depending on the space, you get different things happening, but in general, there's always at least one sort of superluminal polarization state where the phase velocity is greater than c. And that immediately, as I say, puts into question issues of causality, although as I've said previously, that doesn't really rely on the low frequency behavior, it's more on the high frequency behavior. Okay, so before I talk a little bit more about causality, let me just say something that plays an important role in the following. In everything I've said, we're working in the so-called iconal or WKB approximation. So what's that approximation? It's the approximation where the frequency scale is a lot greater than any curvature scale. So R will be a sort of typical curvature scale, an element of the Riemann tensor. So that has mass dimension 2. So it's the limit where the frequency is a lot greater than square root of R. Okay, so even though I'm talking about low frequencies, I'll always still have the frequency a lot greater than the curvature scale. Now, in that limit, in this WKB limit, it's the limit of so-called classical ray optics. So, I mean, I don't want to go into this in too much detail, but the gauge potential in this limit can be written in terms of a polarization part times a phase which involves the so-called iconal phase, capital theta of x. Okay, and in this limit, we can think of the photon as being a wave, but also in a sense a particle, because this phase here, well, if I take its derivative, that describes a vector field in space-time, and the integral curves of that vector field describe the rays, or in fact, the null congruence of photons. So it's important that I work in that limit. Well, for technical reasons, it's very hard to work outside that limit, but it means that I can talk about photons moving along individual rays in space-time. Okay, so this iconal technology will appear later when I describe the calculation. Okay, so let's go back to this issue about causality. So at the heart of it is this notion of causal Green's functions. So, in other words, causality is really, in quantum field theory, the idea of having a well-posed Cauchy problem. So what do I mean by that? Well, it's this idea that we have some Cauchy surface with some initial data for the field, and that then uniquely determines the value of the field at a later point, x. So in terms of points x prime on this Cauchy surface. And that problem is solved by constructing a certain kind of Green's function. It's the so-called retarded Green's function. And causality is the statement that this Green's function is only non-vanishing in or on the forward light cone. So if u and v are light cone coordinates, then causality requires the Green's function is only non-vanishing here and then vanishes outside. And the question will be, can you construct a causal Green's function in a theory where the low energy or the low frequency phase velocity is greater than c? Okay, now this causal behavior of the Green's function, so this is a real space Green's function, puts constraints on the Fourier transform of the Green's function. So for instance, if I just think of one of these null directions, let's pick out V, and then we write this as a Fourier transform with respect to some light cone momentum P plus in the usual way. Then the fact that the retarded Green's function in real space vanishes when V is negative, it's only non-zero when V is positive, means that this Fourier transform here has no singularities in the upper half plane. So this must vanish when V is less than 0. And that implies that the Fourier transform, so the Green's function in Fourier space, P plus space, has no singularities in the upper half plane. And why is that? Well, there can be various singularities on the real axis. So this contour that describes the retarded Green's function has to jump over all those singularities. And then the usual argument is that when V is negative, then I can deform my contour into the upper half plane, and if there are no singularities, then it can be deformed to the semicircle infinity, and as long as things converge properly, I'll get 0. So there's an intimate connection between causality and analyticity, and this P plus will be identified with the frequency of the photon in what follows. Okay, and it's this analyticity which I used in the Kramers-Kronig relation. So I had that my refractive index was analytic. I needed the refractive index to be analytic in the upper half plane to run that argument, and that goes hand in hand with the causal structure of the Green's function. Okay. So the message is that if we want to talk about the causal structure, we need to know the refractive index, or the Green's function, if you like, not just at low frequencies, but at high frequencies. And so we need to go beyond the low energy effective action. So let me talk about the different parameters that I have in this problem. I have the frequency of the photon. I have the curvature scale. Well, okay. Yeah.
So you need to do that if you do not trust what you explained before, right? There were a relation between n for 0 frequency and n at very high frequency.
Yeah, so when I've done the calculation, so here we do a calculation, calculate something. We can then go back and check all this, received wisdom about analyticity and Kramers-Kronig, and we can actually see where the hole lies, if it does lie. Or we might deduce that the quantum electrodynamics is not a causal theory in curved space. So, we do an actual calculation, we can sort of go back and have a look. So we're not going to use any of these properties. We're actually going to calculate the Green's function in curved space. So we have 3 different dimensionful parameters, as well as the fine structure constant. There's the frequency of the photon omega, there's the curvature scale r, and there's the mass of the electron in the loop. And I've already said that we're going to work in the WKB Eikenel approximation, so the frequency must be much larger than the curvature scale. But in order to make progress, I'm also going to take the limit of weak curvature compared with the mass scale of the electron in the loop. Okay, so I'm going to look at the problem in those 2 limits. But that still leaves the dimensionless ratio, which I can write like that, omega squared r over n to the 4th, as a controlling parameter. So when I'm talking about low frequencies and high frequencies, I actually mean small values of that and large values of that. So that's still compatible with, for instance, the frequency being greater than square root of r. And in particular, I need to work non-perturbatively in this parameter because it turns out that the series, if I just work order by order in this parameter, then the series is not Borel summable. So I need to work non-perturbatively in this parameter in order to really understand the causal structure, because it's only an asymptotic expansion. So for instance, a few people have put a lot of effort into finding various terms in the expansion in this parameter or in other limits. But it's no good working order by order, okay, because that won't unlock the problem. Okay, so we need some kind of approach which doesn't expand in this parameter, some sort of non-perturbative approach.
Just a question before you go on.
Yeah.
Why are you not bothered with the logarithms in momentum that come from the fermion loop just on flat space?
Well, why would I be worried about just QED in flat space? And in fact,
Well, there is a sort of logarithmic running of the.
are you worried about the Landau pole issue? And
Well, not even that, but even at low momenta, it seems like it would compete with. But it doesn't.
yeah, it doesn't. I mean, this is logically distinct from that. Okay, there's issues about the running of the coupling.
Are you going to look at your WKB analysis is only going to apply to the effective theory that you've got by integrating out of one loop. When you say Eikenlow approximation, you're not going to sum up Eikenlow graphs in QED.
Well, actually, what we're going to do is going to calculate this one-loop graph exactly using word-line techniques, okay, in the curved background. And we're going to make photon insertions, which, because we're making these limits, we can use the Eikenlow form of the sort of photon vertex operators. So I'm not quite sure how that answers your question, but I mean, that's what we're going to do.
Well, I mean, you can imagine a vacuum polarization graph with corrections in the Eikenlow approximation, which means that you make certain assumptions about the photon approximations of the photon propagators, and you allow essentially you connect photons between all the different parts of the loop. In other words, there is such an approximation.
Right. Well, in this case, we're not thinking so much about that because it's the curve space aspect. So the loop will have to live in curve space. So in other words, you can think about
I understood that.
Yeah.
But you're basically just going to analyze the standard one loop vacuum polarization.
That's right. That's right. And yeah. Okay. Yeah. No, that's what we're going to do. In fact, let me just write down the result of the calculation. And then, depending on how much time I've got, I can fill in the details. So this is the result. And in fact, this is just for scalar QED. I mean, it has all the features of the Drummond-Hathorn effect, and it's not that much harder to do proper QED, but the scalar case is a little bit simpler. And it's a calculation done using word-line techniques. So my refractive index as a function of momentum, frequency rather, well, there's the tree level term, which is, of course, just 1. And it's a 2x2 matrix, remember. And then the one loop correction, order alpha, goes as follows. So there are two integrals. There's an integral over capital T. And what is capital T? Well, here's my electron loop. And because we're working in the word line formalism, it's simply the proper time of the loop. So T. So I have to integrate over loops. So when I've done the calculation, I'll have an integral over this proper time. And then there's the usual factor that tells you the effect of the mass of the particle in the loop. So that usual exponential factor. But then, because I've got two insertions on the loop, because I've got photons coming in and out, I have an integral over like a Feynman parameter, xc, from 0 to 1. And that simply tells you that the first, like the top bit of the loop, has proper time xct, and the bottom part has proper time 1 minus ct. So that explains what those two integrals are. And then this multiplies an integrand which has a delta ij. That actually comes from the tadpole graph. And then a determinant of a matrix delta xx prime, and then the ijth element of that matrix. And I have to tell you what xx prime are. Well, here's the geodesic, the classical geodesic for the photon. And x prime are 2 points on that geodesic, and they're constrained by the fact, so remember that u is the affine parameter on the geodesic, so the point x prime here has the value u equals u prime, and x here has u equals u. So this is constrained to have u minus u prime is twice the frequency t xc 1 minus xc. Okay, so that's the refractive index, but I haven't defined what the matrix delta is. Okay, and in order to do that, I need to define the so-called geodesic distance between 2 points, or in fact, not the geodesic distance, the geodesic interval. Not quite the same thing. That's 1/2 of the integral of g mu x. So a kind of sigma model type action evaluated on the geodesic that joins 2 points, x prime and x. So x prime and x are 2 arbitrary points. There's a geodesic between them, and I'll assume that there's a single geodesic for the moment at least, and so x of tau describes that geodesic, and then you evaluate this sort of sigma model action on that geodesic, and that defines the geodesic interval. Okay, so delta is a matrix which depends on 2 points xx prime, which is actually just the second derivative of this geodesic interval, more or less. Well, I have to raise the indices, but I won't put those factors in. Okay, so it's a very geometrical quantity, and in fact the determinant of capital delta there has a name. It's called the Van Vleck-Moret determinant. Okay, so it's a well-known geometric quantity, and it appears very natural in this calculation. Okay.
Do you look at all the things, do you consider the case where you might have small curvature, but you could have conjugate points?
No, absolutely. Conjugate points play a big role in this. Yeah, so I'll say more about that later. So that's the refractive index. So we can simply take any space we like and plug it in there and look at the behavior. So before explaining how the calculation is done, I mean, I want to do that, but let me at least describe, what the generic behavior in various different situations of the refractive index. Okay, so I mentioned when I was talking about the Drummond-Hatherell effect, for instance, that one example is a conformally flat space. In that case, there are 2 superluminal polarization states at low frequency. So when I'm writing omega here, I really mean this dimensionless ratio. So here's n is 1, the n equals 1 line. And of course, well, let me exaggerate everything, because the effect is very small, it's order alpha. So these superluminal modes at low frequencies, if you look at the refractive index, it nicely asymptotes to 1. So the high frequency behavior is just the normal speed of light c, and it approaches that line like 1 over omega. And in this case, the refractive index, of course, can have an imaginary part, but in this case it vanishes. Okay? So I would claim now that this is showing this causal behavior at high frequencies. The wavefront velocity will be equal to c. The other example I talked about was the Ricci flat case. So that had one superluminal and one subluminal polarization state. So one here and one here at low frequencies. And if you plot these, you work these out, this guy behaves very much like this one here, it asymptotes to 1, whereas the superluminal guy passes through 1, but then asymptotes back to 1. And in this case, the imaginary parts don't vanish, so there's absorption, or if you like, there's a physical process where the photon goes along and creates an electron-positron pair, and these have a typical kind of absorption peak in them, so this is the imaginary part of the refractive index. And the way that this behaves here, this absorption peak, in terms of the frequency, it behaves like e to the minus 1 over omega. So that's why it's, I mean, that's one sign it's no good working order by order in this parameter, because you'd never see this behavior. Yeah.
I'm lost. I haven't understood why this picture has changed now. Didn't you show that if you know omega for 0, n of 0, you know it for n of omega is less than that? So why does it go up instead of down?
Well, that's what we have to address. So this is the calculation, this is the result. And I said we need to go back and look at the received wisdom and find out where the error was. Yeah.
I understand the electron-positron pair production as tidal forces for being produced by tidal forces.
Yeah. Yes, you can. So I haven't actually talked about that, but let me add some comments, because it turns out that the kind of superluminal polarization state corresponds to a situation where the nearby geodesics to the geodesic or photons moving along actually focus down. So there are caustics, that was mentioned before. So the superluminal nature sort of goes hand in hand with like the focusing nature of the geodesics in the neighborhood of the kind of one we're picking out. Whereas the subluminal behavior, it's associated to a defocusing situation. So I think you're spot on by saying that somehow there's tidal forces are kind of ripping the electron and positron.
If you have caustics, if you have conjugate points, doesn't that modify the phase in your Van Vleck formula? Remember, there's an index which is, I think, a square root of I, or counts the number of conjugate points. So in the expression you wrote above for the refractive index, there should be some phase factor that depends on the number of conjugate points you go through. So here you have 2, so that should give you, I think, just a factor of I.
Okay, I'm not quite sure about that. I mean, I'll maybe talk more about that afterwards. What happens is that when you have conjugate points, this sort of Van Vleck matrix, Moret matrix, has singularities.
Right.
So that's.
But there's a way. There's a prescription for taking those into account. I think there's a Maslov index.
The
Maslov index.
Okay, well, we certainly take them into account. I mean, so we're not sort of hiding them, and they play an important role. Okay, so that's the behavior. So then, given that that's the result of the calculation, given that it looks like the wavefront velocity is equal to c, the refractive index goes to 1 at high frequencies, you need to go back and analyze what went wrong with just the conventional arguments based on the Kramers-Kronig relation. But before I do that, let me give some details of the calculation. So I want to finish in the hour, so I won't give many details, but just give you a flavor for for how we do this calculation. So what we're doing is we're looking at a photon traveling along a geodesic. So in order to do that, really, we need to use the language of wave packets and smearing. And so I don't want to sort of get into that because it's a bit technical and it's not very illuminating. So let's just suppose I've picked out a particular photon geodesic. Then at some point, the photon turns into the electron-positron pair, which fluctuate. And so that's why the problem involves sensitivity to the local curvature. Now, as long as that fluctuation is small, I can kind of approximate the whole problem by taking the metric in a kind of tubular neighborhood around this geodesic. And that's why we take this sort of weak curvature limit compared with the mass of the electron, because it's that allows us to simplify the space-time. And what happens is that it naturally picks out the Penrose limit of the full metric. Okay, the Penrose limit is some kind of approximation of the full metric in the neighborhood of a null geodesic, and that's precisely what we have here. So the full metric can be approximated by the following. So there are two null coordinates. U is the one along the photon geodesic, and there's another one, V. And there are two orthogonal directions, the yi's. So that would be the flat metric. And then all the complications of the space-time metric that remain come in a term of the following form. So it's quadratic in the y's, and it involves a 2x2 matrix of functions which depend on the affine parameter along the photon. And in fact, these are nothing but the components of the Riemann tensor, or particular components of the Riemann tensor. Okay, and it's this simplification that allows us to do the calculation, because now we have a problem in these orthogonal directions yi, which is Gaussian, and we can all do Gaussian integrals, even if the resulting determinants are tricky to calculate. So not only does the metric simplify, but it means, for instance, when we're solving for the photon wave functions, this iconal form, that simplifies as well. So the iconal phase, this capital theta, is also Gaussian in the transverse coordinates. So this is equal to what would look like a flat space thing, where P minus and P plus would be my light cone momenta. And the effect of the curvature is then purely in a term which is quadratic in the y's. And there's another 2x2 matrix omega there, which is related to H. So H is minus omega dot minus omega squared. It's like a kind of connection for a field strength. Okay? And hiding inside omega are a couple of integration constants, because I have to integrate this equation. So all in all, this iconal phase depends on, P minus, P plus, and a couple of integration constants. So if you like, these are the curved space analog of just the momentum in flat space, except these integration constants don't directly look like momenta. So I said that we have to form wave packets, so you kind of have to smear at least over these guys to get a photon which is localized along a particular geodesic. But I'm not going to discuss that aspect. But now we have this much simpler metric. We can then apply these word line techniques to calculate the loop. So, and we've reduced everything to a Gaussian problem. So here's our loop of electrons, and we have a photon coming in at 2 points. So this is x prime. Let's call that point x. there's a proper time along the loop, which is capital T, and so this is x of 0, and this is x of ct, and x of 0 is the same of x of capital T. So those are those two parameters, the total word line time and then the proportion spent on the upper part of the loop as opposed to the lower part of the loop. Okay, and the word line techniques instruct me to integrate over the proper time with this factor that I wrote down before, 0 to infinity, integrate over c, which can run from 0 to 1, and then I have to integrate over loops. So that's like a one-dimensional functional integral over the loops with an action which involves the thing that appeared in the geodesic interval formula, where this metric now will be this Penrose limit, this plane wave metric. Okay? Oh, I'm not quite done because, of course, I have to insert the photon at 2 points on this loop, and that's done by inserting vertex operators v of x times, well, okay, depending on parameters, momenta p and p prime at the other point. Take the star there. So what are these vertex operators? Well, they're nothing other than these iconal solutions for the photon field. So they have some polarization part, the iconal phase, and p just stands for this data, p plus, p minus, and these other integration constants. Okay, I haven't described what the polarization part is, but it's very easy to write that down in the plane wave limit as well. Okay, but the whole integral here, well, just to emphasize, it is a Gaussian integral, so that we can just go ahead and evaluate it. And the way we do that is in a couple of stages. We take the integral over the whole loop, and we sort of divide out, or we separate out the integral over 2 points on the loop, so that leaves then the remaining integral over the loop, which is now actually the integral over 2 parts. So we're pinning x prime and x, and then we have these 2 bits of the loop. So let's call that x hat 1 and x hat 2. So we can do the x hat 1 and 2 integrals first, and then do the integrals over the points x and x prime. And it's in doing the integral over the x hats, that's where this Van Vleck-Moret determinant appears. Okay, so we've got our points x prime and x, and it's a Gaussian integral, and it's evaluated around a kind of saddle point, which is the geodesic that runs between x prime and x. So for instance, if I just think about the integral over one part of the loop, that will give a result which will look like the classical action divided by the proper time of that bit of the loop, which is c times t. And the action is simply the geodesic interval. And then there'll be a fluctuation determinant to do, and that gives the square root of the Van Vleck-Moret determinant. Then the integral over the other part of the loop gives exactly the same kind of factor. The only difference is that this 1 over c is replaced by 1 over 1 minus c. Okay, so the Van Vleck-Moret determinant part comes about from integrating out the fluctuations. I mean, and then what remains are integrals over x and x prime. And these are a little bit messy because of those polarization parts of the photon wave functions or vertex operators. So I'm not going to describe those integrals because, I mean, they are Gaussian, so they can be done. But just let me point out that in the plane wave background, this geodesic interval as a very simple form. So it has this overall U dependence and V dependence like this, and then some part that depends on U and U prime and the yi and yi prime coordinates. So the V dependence is very, very simple, and that's because there's a killing vector in the problem in this plane wave background. And so the V integrals are trivial. They just lead to delta function constraints. And one of them just tells you that P plus is conserved, and that's just my frequency. And the other one actually pins the difference between U and U prime. And that's a feature of the result. Remember I said that the 2 points had to lie on the geodesic separated. U minus U prime is equal to this function of T in C. So that's where that came from. It came from a delta function because of the existence of a killing vector. Okay, so collecting all the results together gave the result that I quoted, which I'll just quickly write down again. So there's that integral over T, the integral over C, and then this term involving the Van Vleck-Barrett determinant, where U minus U prime has to be equal to this thing that the delta function sets it to be. Okay, so this was the formula. And one thing that's sort of slightly interesting, well, I find interesting, I mean, it's not really anything to do with curved space, but if you look here, you see that the high frequency behavior of this refractive index, what that means is that you're looking at an electron loop, or the saddle point for the electron loop is a very, very long squashed loop, which is lying along the original geodesic. And as omega gets very big, this loop gets very, very long. So contrary to what I might have expected, the UV behavior of this refractive index actually probes the, if you like, the IR global aspects of the space. So there's a kind of UV IR effect going on here. It's nothing to do with curved space. I mean, the same would be true in flat space. But it's interesting that in order to know about the high frequency, what you would think of as short distance physics, you actually need to know about the behavior of the geodesic in a global sense. And I don't really have any intuition for that, but it's interesting.
You have some small region, and then you boost it. Then the time associated to that thing can become arbitrarily large.
Yeah, I mean, it's easy enough to understand. The thing is, if the incoming photon has higher and higher momentum, it sort of gives a bigger and bigger kick to the electron and positron, and they go further. I mean, it's simply that, but it's kind of unexpected. I thought that at high frequencies you would get a situation where only the very short distance behavior of the space structure would matter.
I think that's only true in Euclidean, and that's where a lot of our intuition comes from.
Right. Yeah. Yeah. That's. I mean, that sounds right, because, as I say, there's nothing about nothing about curved space here. It's just the kinematics of a loop. What was that, Matt?
If you're right on a horizon,
Mm-hmm.
again, so the curvature doesn't really matter, but it's also one of the effects. This is one of the ways of doing Hawking radiation. Some dividing, some dividing light cone that takes it on one side or the other, so the chance of getting out.
Mm-hmm.
Highest frequencies locally are the ones that actually produce the things that make that.
Right. Right. Okay. I like to think about that.
So let's see.
Anyway, it was a kind of surprise to me, but maybe not to you. Okay, so we have this result. In the last couple of minutes, I want to describe what went wrong with the old thinking of Kramers-Kronig and the old style analyticity arguments. And well, this turned out to be rather tricky, and it's to do with this kind of focusing nature of geodesics and caustics, and the fact that the Van Vleck-Moret determinant has singularities. And these singularities appear to give non-analytic behavior. Okay, so let me try to give a sketch of what they do to the refractive index or the Green's function. Let me just think about it as the refractive index as a function of omega. They give rise to non-trivial analytic structure, which has the form of cuts running down in the upper half plane to the origin. And I have to admit, this confused us a lot. And the reason is that you don't really notice these cuts because when you're working to order by order in that dimensionless parameter, because the discontinuity for small omega has this non-perturbative kind of behavior. So you really don't notice these cuts when you're working order by order in omega. And the question is, are they a violation of the usual analyticity arguments that you need to have a causal Green's function? And it turns out, of course, that they're not, because they're not sort of poles or branch points in the upper half plane. So as long as you define your Green's function by a contour that goes properly onto a different sheet here, so it goes through the cut onto a different sheet, then you will have a causal Green's function, because you can still pull that contour off to infinity, to the semicircle at infinity. Okay, so this problem still has causal Green's functions, even though it has this rather strange analytic behavior. Another way to say it is that this is a cut going off to infinity, so there's nothing to stop me really kind of pulling that cut round into the lower half plane. So there is a causal Green's function, even though there's this kind of non-standard, what looks like non-standard analytic behavior.
Physical interpretation of the cut? Is it something to do with some pair production or something? Or?
Well, it arises because of these singularities associated to caustics. So in other words, a geodesic can be infinitesimally deformed because of these. If you choose your 2 points at the end at the caustics, the geodesic can be infinitesimally deformed. There's a zero mode. There's a singularity because of that.
Yeah, that's where this Maslov index comes from, actually. So maybe you've taken it into account.
Okay, so I need to kind of educate myself in that. A lot of these things are very, very old, and it wouldn't be surprise me if some of them were known. Anyway, so then at a sort of nuts and bolts level, what went wrong to Kramers-Kronig relation? Well, it seems very innocuous, but at some point you have this integral along the real axis for the imaginary part of the refractive index, and you write that because the refractive index usually is, the imaginary part is usually an odd function. You write that, as twice the integral from 0 to infinity. Well, it turns out that that's not true because of the existence of this cut. If you like, there's an extra piece which involves the discontinuity at the cut. And if you properly take that into account, then the Kramers-Kronig relation is different because there's an extra term. It's precisely this discontinuity. And that you can then just calculate all the terms, and it is then satisfied, but you need this extra term. So that's how it's consistent with all the old notions. It's just that some of the things that went into the Kramers-Kronig relation were just a little bit too specialized for this situation. So I was going to describe some examples, but I did want to stick to the hour, So there are lots of particular examples you can look at, and we are looking at. So you can look at some space-times which these functions, these are the simplest kinds, where this function that appeared in the plane wave Penrose limit, where these are just this is a constant matrix, and then you can diagonalize it. And these eigenvalues of the matrix, of course, are either positive or negative. And the behavior or the analytic structure depends crucially on that sign. And that's because for the positive sign, well, I'm sort of restating what I've already said, actually. This corresponds to a focusing situation where nearby geodesics focus for that polarization choice. Whereas for H negative, it's the defocusing case. So it's in these cases that you can really get a handle on the analytic structure of this refractive index and calculate everything. So for instance, this matrix, this sort of Van Vleck-Moret matrix, has a very simple form. It's diagonal, and it's simply equal to the following. So when the HI's are positive, you have trigonometric behavior, and that's what this is showing here. So that you get these caustics appearing, and when the HI's are negative, then this becomes hyperbolic, and that's when you get this sort of defocusing behavior. And the analytic structure is very different in both cases. And then other situations, things we're thinking about at the moment are shockwave situations. So that's where this plane wave factor is like a delta function in U. And those situations also have interesting analytic structure. And the other things that one can think about are to put fermions in the loop. So that complicates things a little bit, but I don't think it'll change the conclusion that QED in curved space is a causal theory, but it has interesting structure. The phase velocities at low frequencies can be greater than c, but that's okay. That's consistent with causality. Okay, I'll stop there.
Well, what about the obvious spacetimes of ADS and DS? What do you find in those cases?
Well, I mean, so those spaces, what really matters is the Penrose limit. So, you know what the Penrose limits of those spaces are.
So what values of H do you, presumably you get one choice of one and not one for the other?
Yeah, so the basic physics then just depends on whether there's a plus sign or a minus sign. In some situations there are pluses, in some situations there are different signs. But the kind of generic behavior is, will be one of these two. And you could just choose your space, look at the Penrose limit, and calculate the refractive index.
From the point of view of the low energy effective theory, can't
I guess the conclusion is that it's hard to draw conclusions by looking at the low energy effective field theory. There may be superluminal propagation in that theory, but it doesn't mean to say the theory's sick, because you just have to go beyond the low energy effective field theory. You have to work non-perturbatively in the frequency. So that's where I started by saying that it's been suggested that if you find superluminal propagation in a low energy effective field theory, it means the theory is sick. It doesn't have a UV completion. And well, hopefully QED does have a good UV completion, so this is a counterexample.
What's it to scale in exponential minus 1 the electron mass?
Oh, it's always this dimensionless ratio that I'm talking about. So when I write omega, really I mean r omega squared over m to the fourth, or at least the square root of that. So it's a combination of the curvature and the mass.
Thanks, Jim.
Thank you.